before we started, we seem to have a bit of connection issues because of the wind. That's not so nice, but we'll hopefully be okay for now. So this is the second part of the seminar that I've put together, and in our first part. There we go. In our first part, what we spoke about was we discussed some of the basics of the experimental design, and here we had to pay a lot of attention to issues like treatments, what is replication, and particularly what is randomization. Then I thought that I will give you a little bit more background at that time about what hypotheses really are and what it actually means when we look at p-values. And I gave you a very brief introduction on some aspects of regression analysis, particularly the topic of what is a correlation and how do we distinguish between a correlation and a causation. That was a preliminary look. There was just one issue that I pointed out. And this particular part of statistical analysis, which is correlation and causation, will actually play quite a much larger role today, because it will come up in a whole lot of different ways of looking at things and from different angles. So for today, what I wanted to discuss with you is what is causation and how can we learn better to interpret results. I will give a little bit of an idea about what is the quality of data, what's the validity of data. For example, what is a good data set? What is how do we deal with data sets when we discuss issues like precision and accuracy? And a rather important concept that I will continue with is the concept of biases. Biases are really essential, and they have to be seen for what they are, and they have to be appreciated for what they do when we interpret our results. A topic that might interest some of you, if you already have data or data sets that you're working with, is the relatively difficult question about what are outliers. Of course, outliers, that is implied in the word, are data that don't actually fit your normal averages, but you will always be asking yourself what you actually do with them, if anything, how you handle it, and how you respond to the fact that you might find outliers in your data sets that are, by definition, rather unexpected. And as a last point that I'd like to bring up is a few ideas on scientific writing that have to do directly with data analysis and interpretation. Let me see whether we can have a little bit more of a brainstorm session and a overview and some background on the topic of causation. The topic of correlation is basically mostly well known to all of us somehow, and correlation, as we know it, looks mostly like this. There's a graph here on the left that shows you what we call a relatively good positive correlation between two data sets, an X and a Y. So usually the axis is plotted on the x-axis, and the dependent variable is the dots that you will find as a response to X. So each pair is a data point. This will be a good positive correlation. You can also get good negative correlations. In other words, the fact that the correlation is negative, that doesn't make it bad at all as long as it's strong enough. It can go the other way around too. But look at this graph that is sitting next to this, and you'll get a much different idea. Here, if we were to do a correlation analysis, statistical test that tests for correlation, we would in all likelihood find a correlation coefficient of 0. In other words, the statistical test does not actually tell us, or it misleads us and tells us that there's no correlation between those data. And the reason is that the testing is assuming that data are linearly correlated to each other, like in more or less straight lines, or sometimes also in the form also in the form of exponential curves, but not this kind of curve that I'm showing in here. So sometimes a trend in data sets actually exists, but when we do only the statistical analyses, then we will easily see that we can be misled or sometimes overlook something. So one of the key points that I'm bringing up and that I will also bring up repeatedly as we go along today is that no statistical testing should ever be conducted at all until you first look at the data set. And what I mean with this is really just the concept of looking. There's no test yet. You just want to see what trends you're dealing with, because if you don't do it, your test in itself will give you a lot of different answers that might not even make sense. So visualize data and then continue from there. So a first step maybe to address the whole topic of causation and correlation versus causation is that we must be very much aware of the fact that we have, in almost all experiments, confounding variables. A confounding variable is a very complicated thing. It is basically a kind of a variable that makes it look as if there is a correlation between two other variables, but the confounding variable is the one that masks it. In other words, that can give you the wrong idea about something. Here's a simple example. There was a study that compared health status of people that took vitamin supplements with a group that does not take the extra vitamins. So you can see that's quite a simple design. You've got a control group and you've got a test group or a treatment in which the vitamins are taken and the other group has its normal diet and normal nutrition. The outcome from the study was that people that took the vitamins were overall having better health assessments. So whatever was tested there is at this point not really the most important thing. They may have tested blood values or they may have tested people's heart rates. Doesn't matter at this point. But it turned out that from this study, the people who took the vitamins were healthier. Can we, based on this, argue that the outcome of such a study was actually due to the vitamins? In the first simple look, we might be easily deceived, and we might say to ourselves that it's obvious the one group took the vitamins, the other one didn't. So it can only really be that. So let's make a list of potentially confounding variables that we can come up with. Those are examples. At the end of the day, you may find even more examples, but these are the ones that I hope are making it a little bit clearer. So the questions that we might have about the variables of your study is, are we sure that people were randomly assigned to the groups, or perhaps did they volunteer? Maybe people who volunteered would have liked to be in that group who took the vitamins, and they already not anymore a randomly chosen sample, just right there. And perhaps whatever their results are might not anymore be due to vitamins, but due to other factors. For example, did people who took the vitamins before the study did they have healthy habits? In other words, were they already predisposed to have a better outcome, and the vitamins may not even have made a difference? Were the data randomized for age, for gender, for any pre-existing conditions, for diet, etc.? We don't know until we actually do the study properly, and we can already say that we have randomized properly. So I'll give you an interesting numbers example. Let's say we would wrongly assign to a vitamin group to a higher age class, and let's say that under normal conditions, the higher age class would have, say, a 10% lower health than the younger age class. Now, if the vitamin effect is really approximately 10%, then our results would show that these two factors cancel each other out, and we would not even find an effect of the vitamins because it was already masked by the fact that the subjects weren't randomized to the treatments. A similar thing can be seen for gender or people who have always preferred a different diet, etc. So whatever their results would be, or whatever their health status would be, must not interfere with testing the real thing, which is whether the vitamins worked. So if a study doesn't account for confounding variables, or if we don't have the right sampling procedures, then it's unfortunately the fact that results cannot easily be trusted. There's many more examples of those. So considering that if we discuss these issues, what can a test for significance actually tell us? Because that is something we often like to overlook, or we're often not actually interpreting in the way that perhaps we should. The first thing is that any test that you use to test for significance is based only on data from samples. It's never the whole population. If you had the whole population, you actually not need a test, then your data is right there. There's nothing to estimate, you know what. But we don't hardly ever do have a whole population of anything. So we use samples, and from that, we draw our conclusions. Sometimes sampling errors or small sample sizes can even give you the wrong picture. Previously, I just discussed in the last slide how sampling errors can go things wrong, and sometimes very small sample sizes, we're going to get to that, will give you kind of the wrong idea. You don't actually know anymore what it is that you're looking at. So those very annoying confounding variables that we have in just about any experiment, how can we control those? I brought it up already. A part of control, a big part, is randomization. A second part is potentially, I'm going to explain it as we go along, so-called quasi-experiments or pilot studies. And it's also important to understand commonly encountered biases. And we'll get to the biases as we go along. So one more thing about randomization. Subjects must be assigned to groups randomly. For that, you can use super simple methods. If it's a smaller study, you put names into a hat and you randomly pull them out, just the old-fashioned way, like in a lottery or something, and you assign subjects randomly to groups. Your spreadsheets, your Excel spreadsheet, for example, can also give you random numbers, and that's great. So you do the best you can to randomly assign subjects. Also, collecting data is very relevant. If you, for example, collect data about people's habits for what they would like to, how they would like to spend their day on a specific activity, then it would certainly make a big difference whether you collect data from people through a questionnaire only in the morning time, and then you might get the whole wrong idea about what people would be answering. And then you must make sure that any additional variables that you can collect can be used to further estimate what effects you would be having on, what effects they may be having on your data set, on your results. Another interesting question is, you must sometimes ask yourself, if you do, say, surveys, or if you deal with observational studies and checking people's habits on something, for example, whether tightly controlled conditions are actually the best representation for real-world conditions. A very nicely, very tightly controlled experiment in which everybody comes to a lab and gets tested on certain interests that they have might give you a very different outcome from testing people's normal conditions by randomly sampling from there and having them exposed to their day-to-day routines. So even a very good and tightly controlled experiment may not actually be the right thing that you want to use to answer your questions. And of course, random assignments can be will always be tricky when it comes to ethical issues. Say you want to test a certain kind of medicine that treats people's disease. It will always be a very challenging thing to decide who should be in a control group to not get a medicine. We can't go into too much details on this. I'm just bringing it up here because it's such a well-known and extremely difficult issue, is how you assign people randomly when you have potential disadvantages for some people, which are ethically not acceptable. A lot of pharmacy experiments deal with this on a day-to-day basis, and they do find ways around, but ultimately it will always be something that comes in between your experimental design to make it super perfect, but you cannot make something super perfect if it has collateral damage to people. So that's obviously something that one should never forget. As a possible solution that people have come up with is so-called quasi-experiments. Those are more like pilot studies. Before you do a proper big study and you want to find correlations and causations between data, you sometimes make an experiment in a well-controlled environment to find some causality between data, but you may not always be able to properly randomize. You collect as many variables as you can possibly can, and then you use whatever statistical methods are a bit more complicated and comprehensive to try to model and estimate how your data can be explained. Why can you not always randomize? Sometimes in some conditions, you want to test people's behavior, and it turns out you only have a certain age group available at a time. Then rather than trying to get a wide range of age groups, just consider that for now, you're going to just use a limited kind of data set, and it will at least give you some identification about factors and some hint about where to go from there. So quasi-experiments aren't all that bad, but they're harder to analyze in the bigger picture because they don't always account for everything that you need. They have benefits, and that's that they might help you find and design more controlled studies or better randomized studies at a later stage. But as before, causality may still be difficult to find. So this kind of problem will never quite go away, and it is something that we deal with all the time, and we have to be quite aware of the fact that we should never forget about it. I wanted to give you an example of an experiment that was actually done. The reference is on the bottom of the slide, and it was quite a simple study. It wasn't the most, maybe not the most earth-shattering study in a big way, but it was relatively well done. It was well randomized. The data were good controlled. The biases were taken care of as much as one can do for such a study. And the background for the study was actually quite straightforward. The researchers, this was a psychology study, they offered certain chocolates in a university cafeteria, and they labeled them. So that was factor A. They labeled them as the original version, and they labeled them as one that was called reduced calories. Then they took a second factor into account, which was the people who actually went to the cafeteria, the consumers. And they divided them roughly into two groups. One was people who could be considered happy with their weight, and another group would be those that would maybe like to lose a bit of weight. I've often wondered, but I suppose I probably find myself in the second group as well. So these are just more or less two distinctions that were made, and the dependent variable was the consumption of the chocolates. Seems like quite a straightforward study, quite a interesting one to test. And before you go any further with any kinds of experiments, you need hypotheses. We've just discussed hypotheses in last week already. So now maybe it's going to be a little easier now to do it in a more shorter way. So we have three null hypotheses in this experiment because we have two factors. The first one is that the null hypothesis would be that there's no difference in average consumption between chocolates of different labels. That was the regular versus reduced calories. The second hypothesis we want to test is whether there's no difference in average consumption between the two groups of people. And the third one is whether there is a significant interaction between these two main effects, which is labels and groups. That is a more difficult one, and I think the best way to do it is to make a graphical representation about what kind of results the people found. Let's first look at the ANOVA table. That's the sort of thing that you get out of your statistic programs. And here we have the factor A, which is the food, which is the food label. And we have a p-value that is well below 5%. And that p-value then would indicate to us that there would be a significant difference in average consumption between the two food labels. We have the two groups of people. We have a p-value of below 5%. And that indicates that one group of people would have a higher preference for in their consumption than the other. And then we have what is called the interaction, which is a combination of the two together. And the interaction term is a difficult one to interpret, but it is extremely important to know it. And it brings us, as we can see in a moment, it brings us all the way back to that whole question of correlation, causation, and reasons and interpretation of data. So let's look at the results. This is graph number one. On the y-axis, you see the amount of calories consumed, and that would be the average of all the original and the average of all the reduced calories that were offered. So people would have consumed more of the reduced calories in average over both groups. Okay. So you kind of, there's a bit of an expectation here. It could make some sense that consumers would say, oh, this is something that has reduced calories, so I can maybe allow myself a few extras. So far, so good. Let's continue with our hypothesis test and our interpretation of the data. This is an average of the two groups. On the bottom is the ones that are more happy with their weight. On the other ones, it's the one that would like to lose a bit of weight. And here we see that the lower consumption in average between the two groups was the ones that were happy with the weight. So by now we will ask ourselves, did we, up to this point, actually learn anything from this statistical test and analysis? Unfortunately, not really, because we haven't yet looked at the combination of the two. And here is the graph of the same data nothing different, just graphed in that way that the combination is done together. And this is now for the first time that we get to appreciate what an interaction term actually tells us. So in average, between the two groups, which is either the blue and the green line, the consumption for original was kind of similar. Yet, when it came to the consumption for the reduced calories, it turns out that it was then the blue group that had the higher consumption. So that means that that comparing averages between the two types of chocolate or averages between the two groups would actually be missing out a huge amount of information, because here you can see that one depends on the other. And that is what we mean by interaction terms. So I don't know whether it might be a good time for a couple of questions at this point, because we discussed earlier that maybe we should have those smaller breaks. Sharon, if you're in right now, let me know what you think and whether there was anything in the chats.
There aren't any questions in the chat so far, but we can give you sort of 30 seconds to think of a question if you have one, and you can either type it in the chat or you can unmute your microphone and ask Professor Kaiser your question directly. Does anybody have any questions?
Either way is fine.
Or do you want us to keep going?
Either way is fine with me.
Any questions, or
Is everybody thinking about going? Is everybody thinking about finding that chocolate?
Maybe. Okay, they're happy to keep going for now, Horst.
100%. You can always interrupt, no problem.
Okay, no problem.
So you will see where we are. This graph may not really look as if it's directly related to correlation and causation, but ultimately it really is the heart of it, and that is that understanding a part of a data set often requires us to know combinations or other data that can influence what we see. This is a relatively straightforward and yet still quite interesting example. So until now, I've done what you would call relatively well-controlled experiments, like designed. They were set, and subjects were maybe chosen for something, or animals were put into certain groups, or this kind of stuff that we know as being well-designed controlled studies. We can't often do it, and that is not necessarily a bad thing, because there's alternatives. And one of the alternatives to that is what we call observational studies. Observational studies are more, I would call them, they're more informal in a way, that not everything is always set up front. So not all designs that we have allow in those observational studies, not all designs allow for really good control of variables. You can have an observational study where you maybe observe people's behavior at an airport. They come and go, and you cannot necessarily have a specific group that you ask to stay there long enough until you've seen everything. So you literally have to deal with what you got, and you have to control your variables as good as you can. You can write down at what time you observed something, what gender you looked at, or whether people came from an incoming flight to an outgoing flight, and you collect as much as you can to learn about how people respond to certain things. We often have only the observations directly, so we can't really have planning or an interference. We shouldn't actually, because then we will mess it up. And we're not always having an exactly highly desirable random assignment of subjects. We just have to know we take what we can get. So those kind of studies can actually be good alternatives to controlled studies. And here we can use some statistical methods that are a little bit more complex. We don't discuss today here, and they can be used to maybe try to estimate confounding factors as much as possible, so that they change from confounding factors to actually predicting factors. There was an interesting observational study that was done some time ago, where a very famous violin player in New York had just given a massive concert the previous day, and it was thousands of people attending at high prices, etc. And the very same violin player actually decided the next day to play the same piece again, most complicated piece you can imagine, and he played it at an airport, and the scientists were observing how many people actually walked by, or how many people stood and listened. And it turned out that only 1 or 2 people actually stood to listen. And at the end of the day, he made about $5 or something as a tip. And that was like one of the best people to play this kind of music. The reason why people responded in that way was because they did not expect it. They had other things on their mind, and they weren't really ready to look carefully what was in front of them. So with observational studies, we always have to consider that we can find sometimes very, very interesting and surprising outcomes that teach us more about people than we may have thought. So they're positive things. There we go. So two more slides about how we can distinguish between criteria that help us establish causation between elements. For example, if you relate values to each other and you have very high R-square values, in other words, a very high correlation, that does not give you a full guarantee that there aren't any other factors involved, but it is quite high. And if it is high and consistently high, it might already give you an idea that maybe other factors might not be as strong in influencing your data as the real data that you're testing. Then the next thing is, if you find certain things, then are they consistent? In other words, have other experiments found relatively similar outcomes? Not the same, never is the same, but the question basically was whether what you find could be reasonably expected. Then causation is still not solved completely, but it gives you one step further to think that the data you found might actually be reportable and meaningful. So then if you do a comprehensive analysis and you combine your data with those from the literature and the method that you did use, can you now find any possible factors that may have messed up your data set to such an extent that you don't have correlation, but rather other factors involved? Maybe. A relatively simple test is, can you trace whether a cause occurred before an effect? If, for example, you provide a certain medicine to people and test their blood pressure afterwards, and if it's always first the cause, the medicine, then the effect, the blood pressure, with as much control as possible, you're again one step further in figuring out whether the correlation you have is about as real as you would hope it is. So that's similar to dose response studies. In other words, if you increase a certain thing, then, for example, again, say, if you use a certain medicine and you increase the dose and you get a reliable response to that, more of this means more of this, more of this means more of that, then not perfect, but again, you have another step forward into finding out correlation and causation. Is the result plausible? Do you find anything that is completely out of the ordinary? then you may have to carefully look, and you have to think what could have affected something. Are there similar studies with similar conclusions? Then you're coherent with what people have found. And of course, the whole thing is that I've mentioned earlier is have researchers actually used randomized experimental methods. Very important. So we've discussed the issue of causation and correlation from all different kinds of angles now. And I was hoping that at this point you can see how important it is to interpret your data analysis so that you have the right kind of outcome, that you say you're right and say the right kinds of things that are really as true as possible to your data. But what we haven't really discussed quite yet is the data themselves. What are data? It's something you collect in most cases. It's something you observe. It does not always have to be numbers, but it most often is. And sometimes if you have frequencies, they can be turned into numbers. Percentages can be changed in numbers. So if you're lucky enough that you have numbers, then at least you can work with that. So what are the four groups or the four kinds of groups of data that we look at? They can be basically distinguished like this. The real average in your data set, the one that you obviously don't really know at this stage, but the one that is likely to be a representative average of your data, is in the middle of the cross. Upper left, you may have data that are quite accurate, but have quite a variability. So they're accurately describing the average, but they may not be terribly precise. To the right of that, you have a data set that gives you a very good representation of an average. And it also happens to be quite accurate at the same time. So that is precise and accurate. Bottom left, you might have data sets that are really not accurate at all. So the variability is so big that you cannot easily estimate what the mean should be. And by definition, they're also not likely to be very precise either. And bottom right, you may have a situation where you have really precise measurements, but they're not accurate. That's a tricky one. It's possible sometimes that you use scientific instruments that for some or other reason just haven't been calibrated quite right, and they always give you a consistent error on one side. So your measurements are actually still all right, except that the values are wrong. So if that kind of thing happens, you might have perhaps a chance to find out what factor it is that has changed your data, so that you can maybe go back to the top left, which is, or the top right actually, which is precise and accurate at the same time. These are the four kinds of groups of data that you look at when it comes to accuracy and precision.
Can I interrupt really quickly while you take a pause here, because there's a question that is pertinent to this slide, maybe before we move on. And the question is, what is precise and what is accurate when we're talking about data?
Well, as you see in the picture here, for example, the top right, precise would mean that you are having measurements with a low variability. So you have measured with a high precision, but it doesn't necessarily make it right. So you might have data that are giving you a good idea, an accurate idea about your averages, but still with a lot of variability around it. If worst case scenario, I would still have rather this, because it gives you some estimation of your average value. Best is when they are really well done and hit the average. But sometimes you might have data sets that are precise, but that means that they're very low variability, but they're actually off the average of what you would expect it to be. These can be consistent errors that just hit it all the time, and then you end up having the kind of data set that gives you a wrong average, but it still gives you a good idea about how data are distributed. That is it okay with this? Could this make any sense?
James, does that answer your question? Grady has a follow-up question. Then what should we do to get data that is both precise and accurate? I assume you're going to move on to talk about this now.
Yes, in fact, I do. That was part of the plan, but the answer is so multi-layered that the next slide only is not going to answer it all. So the first thing is that depending on what your experiment, how your experiment is designed, you make sure you control as many random factors as many factors as you can through random assignment of data. Say take the bottom right graph, and say you wanted to test specific behaviors in people, and you would have maybe taken only one gender. Then maybe all of the data that you got is very accurate for that gender, but is actually off the average because you should have maybe tested the other gender as well, or whether it's adult people or children, etc. So you make your assignment of subjects as random as you can to help out with those factors that can influence your data. And the second point is also quite relevant, and that is this one in this graph here, and that has to do with the fact of sample size. Sample size is something that probably all of us want to know, and we all want to think about how to deal with it. So as a general rule for continuous data, by taking all our data together, we should get what is called a normal distribution. A normal distribution is an equal distribution around a specific mean. And here we have a graph with three different colors, and the blue one, the tallest one, is the one that is based on the highest sample size, and the gray one on the bottom is based on a sample size of 5. So now what happens is, when you have, this is relatively easy and intuitively helpful to understand. When you have a very low sample size, you will be missing out on accuracy and prediction. And you might have just by accident sampled the five data points that are the most out of your normal distribution. But you wouldn't know because you only have a small sample size. If your sample size then increases further, your frequency distribution also changes, and the variability around the mean gets smaller. So these three color bar chart, these three color histograms have the same mean, just a different variability around them. And they are, of course, drawn as estimates of a normal distribution from your samples. So that gives you a good idea about sample size themselves. To come back to your question, in statistics we have what we call the so-called effect size, and that is the sample size that you should be having. You can calculate this, that you should be having in order to confidently test your null hypothesis. The problem is that we do not always have that sample size available, and depending on the variability in your data set, it may sometimes turn out that sample size has to be quite high. So that doesn't yet mean that your experiment is a complete disaster. It only means that you have a lower power in terms of being sure that you are properly rejecting the null hypothesis. So so this is basically the issue about precision and accuracy, and about what we can find in our data sets. So effects are, I'm finally finding out what the chat say. So effect size and power of test. Effect size is basically referring to the fact that how many samples of a population do you need so that the error in rejecting the null hypothesis is about as low as possible. And in other words, the more the higher your sample size, the more is the power of your test that you be sure to make a right decision. We don't want to go now into major hypothesis testing issues about false positives and false negatives, but I think as an intuitive thing or as an overall idea, these are the two things that you have to consider. The effect size is something that can be calculated upfront using some of the variability in your data. And people often do it, but very often also people don't, because they already know that they might not actually have quite as many samples available. You can still do your study though. And this is why you have the uncertainty about your results. And this is why sometimes a specific p-value that comes up is maybe not quite the right thing for your data set, unless you go ahead and increase the sample size. I hope that will give you some idea.
There is just one question from James here. Grady says, thank you, you have answered his question. But there's just one more question to just clarify a little bit what is meant by effect size and power of test. If you could maybe address that as you move on.
Yeah, the effect size is that sample size that you would need to confidently reject your null hypothesis. So if you were to take, say, out of a group of hundreds of people, and you would maybe let's make a simple concept. Let's take you have hundreds of people and you want to have their average height. And you decide to take 3 people out to measure their average height. Then it turns out you get an average from those 3 people, but you have no idea yet whether that is actually a good average for the rest of the population. So you would then have to see whether you can increase your effect size, which is the sample that you're using, to such an extent that you have a better confidence in getting the right answer to your question. For example, in this case, what is the average of something? And the power of the test is basically has to do with how confident you'll be able to do that. If you want to learn more about this, you can basically look in some of the stats books or maybe on the internet, and you can look at the distinction between what we call an alpha error and a beta error. An alpha error is the usual 5% that we need to find out whether we should accept a null hypothesis, and a beta error would be the error that you do when you don't accept it, but you should have. So this is a more complicated topic that is maybe well worth a seminar in its own rights. Yeah, that is simpler than textbooks. I do like to do it like this rather than throwing lots of formula at you, but this is basically what the whole idea is about it. Okay. Okay, I think I'll continue. I have to click here. So biases. Let's talk a little bit more about biases, because they're very interesting things. Observations. Okay, not everybody must now write in their chats what they see, but bunny or duck? No, duck. No, bunny. So are we accepting the fact that we all should disagree on it? Or perhaps, what would have happened if I would have told you upfront that the next picture is just going to be a drawing of a bunny. What would have happened if I'd done it the other way around? So a very important sentence, which maybe the one sentence that I would like you to take with, is the sentence, believe what you see and don't see what you believe. It's life-changing in a way. Believe what you see, but try not to see something that you actually should be seeing. If it's not there, it's not there. End of story. So the bias in observations, the first one that I'm discussing with you is the simplest one, and that is, what do we see, and do we actually have a preconceived idea about what we see? Perhaps if there's maybe one thing for your life that you want to take with, then it's this particular sentence. What might happen? I'll make a short prediction. What might happen is that you now say to yourself that you understand this statement that I'm making. And maybe in a year from now or 2 years from now, you might find that you're looking at something totally unrelated, and suddenly, when you least expect it, you will have that moment when you think, yes, I do now understand what this means. So I won't expect it to be clear immediately, but it's probably one of the most important things. So what does this kind of observation bias do? Sometimes we look at things under a microscope and we look at information that we actually want to see, and we will see it. We don't want to look further all of a sudden because we saw what we expected to see, and therefore we already have a major observation bias that we have to deal with. Sometimes you may do an experiment in which you expect people to do certain behaviors, and by the time you go through your data set and you realize that you pretty much got what you thought you might be getting, you might be tempted, but you shouldn't, to just say, oh, let's call it off now because I got what I wanted. So a good planned experiment is the one where you actually make sure that there isn't a problem with this kind of thing. And sometimes even more interesting is we sometimes may ignore findings that we might consider unimportant. We sit there and we see something and we think, nah, it cannot be. Let's forget. An interesting observation bias that went into history was that in the early days, when the first counts were done of chromosome numbers in humans, it was always 48. And then for decades, the next people who did chromosome counts also counted 48. Until somebody says, come, let's have one more look. There's only 46. So people were expecting what they wanted to see. And there it goes. Before you knew it, the information wasn't changing, but it was still not the right one. So from the observation bias, I moved to what is called the survivorship bias. That's a really tricky one and a very, very interesting one too. A survivorship bias is that we sometimes have only information on successes. If you look at advertisement, you look at weight loss data, you see how many dozens of people in an advertisement make a big story about the fact that they've lost a lot of weight on a specific diet. Clearly, the ones that didn't lose weight aren't coming forward with this. So you have the wrong sample and your survivorship bias, meaning that those that made it into something is actually biasing your views. Here's a good one. Does dropping out of college make you successful in business? I could be wrong and say, of course it does. It did it for Bill Gates, Steve Jobs, and Jeff Bezos from Amazon, from Apple, and from Microsoft. They all dropped out of college first and then became successful in business. And you would say, oh, that makes a lot of sense. So therefore, let's conclude that this is a good basis to be successful in business. Well, of course it isn't, because those that dropped out of college and didn't become successful in business aren't listed here. A very famous example that I want to quickly bring up with you is the one about World War II airplane analysis. This is a real thing. The next slide is going to show you what happened. And what happened is the following. the British were losing airplanes in the Second World War, and they employed statisticians to actually look at where those airplanes were hit. Now, he had available, of course, the airplanes that came back to the army. So he looked up what is the distribution of where the airplanes were hit, and he got the distribution of hits like it is shown in this little picture. Then he was asked as to where he should be reinforcing the airplanes to make them safer. And he answered correctly by saying, they should be reinforced in those spots where I don't see hits, because I'm only seeing the airplanes that came back. The ones that didn't come back, if they had the same distribution, they would have been hit there where I don't see those dots. So it was the missing information that provided the answer to this particular issue. The very famous example, and he was actually quite right about this, and it turned out to be fairly complicated statistical analysis, yet it actually explained that quite well. So sometimes what's missing is what's telling us something. Then we have selection bias, which is, for example, I've mentioned before, people volunteering for a study. Are they a representative sample, or are they just there because they want to be? Then we have surveys and people who don't respond. Maybe they have a specific information or bias in them that doesn't make them respond, so you're missing out on data set. Then you have what we call temporal sampling errors. That is the sort of thing where you sample at the wrong time. Must be randomized. And then, of course, as always, randomization. Here's an interesting one. It's the so-called paradigm-based bias. Paradigm-based bias is that sometimes by information we have and theories we have can be very, very tough. They can be quite tenacious and they don't like to be changed. So if your experiments find something that doesn't exactly meet that expectation, then sometimes you might not want to see the facts that you have. And if they don't fit into a paradigm, you may feel like you don't necessarily want to mess with the big authorities and say that you found something different. It's a big effort. So a lot of paradigms in science have actually stayed where they were because smaller studies that didn't quite have the courage to come forward with what they found were kind of still buried underground for a long time until more and more people came along and say, oh, but we also found this and this and that. And therefore, we now know that we must maybe change our theories a little bit. There's lots and lots of those examples. The next slide I'm bringing up with you, I'm not going to discuss this in a lot of detail. And there's a reason for this. And the reason is simply that it's too difficult. It's too difficult for just about everybody involved. What happened here is that a group of statisticians wrote a paper in Nature in 2019. And they made a big point of saying that we should maybe not be so strict about the 5% p-value level, but rather employ some other ways of looking at things and not be so stuck to that 5% cutoff. So that's the simple way of explaining what this paper did. What they then did is they did something very interesting, and they actually sent an unpublished draft of their ideas to statisticians around the world. And within just 1 or 2 days, they had more than 800 people who are professional statisticians to sign on and say, we agree, we always thought so, but we never said it. So what happened here is that this is still very new. This is literally only published, like, if you want to say, a year and a bit ago. And I think that there may be some changes coming at some stage where we really have to reconsider a few ways of how we deal with stuff. I'm mentioning it because I wanted it to be complete. And I want to make sure that I'm also showing the other side of things. And it's a very good paper. If you ever feel like you want to read it, it's very simple. It doesn't have a lot of numbers and formulas in it, but it makes a point very nicely. So that's something for controversy and for thinking about stuff a little bit closer. Next point, outliers. If you have collected data for yourself yet, then yeah, you may have found them, like this. You may have had 4 treatments perhaps, and they have averages and they have means and medians. And then they always have a couple of data that are just way out there. What do you do with them? Do you ignore them? Before I go further and explain a few more things about it, the simple answer is no, you don't ignore them. Because you cannot yet know whether they have information in them. In some simple cases, you can maybe ignore them. If you find a data set that people have put together on the height of people and you have like one data point in there that gives you 10 meters, then you kind of an idea that maybe that's a typo. Maybe it should be 1 point something meters, you know. But you don't know where the cutoff point is. Here in this particular example, in treatment number 3 from the left, I've got 2 outliers. If I take the higher one out, then the second one below it becomes an outlier again. So do I then take this one too? So this is a difficult question. So they're tough. So look at the regression model. The left and the right, the left graph and the right graph have the same data set except for 1 point. In the left graph, there's 1 outlier, and the regression model isn't even a significant model. And in the right graph, I've taken the outlier out just to test and to show you the effect, and we suddenly have a significant model. So here we go. We have a very interesting kind of a challenge about what we do with hypotheses, with outliers, and I'm going to go and explain something about that now. But I see some chat. Can we consider a bias as a possible hypothesis to launch a study? That's great. I love a question. I love a question like this that also makes me think a bit. The bias is a possible hypothesis for a new study if we have identified it as being a bias. By the time we know that it is one, we could actually then go ahead and redesign a study to exclude it. If, however, we have a study and you have analyzed the data set and you are not yet aware of the fact that your interpretation may have been a result of a bias, then you're kind of stuck there, and it bites itself into its own tail, and you can go and continue there. But by identifying them, you have an interesting hypothesis for a future study, but it must be properly based on the data that you have. What could be the best approach with a data set where there's too much treatment variability, yet culture conditions were similar? Well, here, NASA, we've discussed it before many times, is the best approach is obviously to attempt a higher sample size or to repeat the experiment. All right. So the next question, and that's I like the fact that this come up. It was very mechanical to remove the outlier. Yes, that's why I did that on purpose, because I was going to explain to you in the next slide why this matters and why I shouldn't do it. I did it only to show you what an effect it can have. So let's look at the conclusions that we can come up from outliers, and maybe I can then make it a bit clearer as to what my own views are. So the most important, crucial thing is, before you conduct any study or any data analysis, always, without exception, visualize your data points. Don't just crunch numbers in a spreadsheet or something. Just look what you got. That's a huge thing. So there are tests to detect outliers. So it's not that is a mechanic. That is absolutely true. And they rely strongly on the fact that the data are actually normally distributed. Sometimes you don't even know. So as a recommendation is, understand your data, and the distribution of the data sometimes differs between disciplines. For example, in a factory that makes screws or nails or something like that, you would mostly have a very low variability in your data. Only every few thousand times a small piece breaks off, and then that is just being discarded. In a data set that has maybe a data set about human behavior, you might sometimes have such wide variability that you should be very, very cautious of just assuming that an outlier is really an outlier. So then the next step is you investigate your data and your methods. Could there be an error in the data entry? If it is sometimes super, super clear that there is, leave the spreadsheet as is and make sure that you report what you found. Don't just delete it and let it go away. So what I showed you in the graph was the regression analysis, was a demonstration to see what actually does happen when you do it. Yet I did not mean it to be the answer or the correct solution. I meant it to be an example of what kind of effect it can have. Then you must look at what's the precision in your methods. And you must sometimes see whether there is actually possible valuable information that you can learn from an outlier. So outliers, in my opinion, should not be deleted. They should always be discussed, and the action upon them and how you report them is crucial. So I hope that I didn't give you the wrong idea by just deleting the outlier from the regression line. I just wanted to only demonstrate to you what can happen if you do. That doesn't make it right. So having done this part, I have two slightly shorter sessions, and here I must admit that we have talked so much about bias. Here I must admit that I've picked out some of the writing and report writing sentences that I find particularly worthwhile mentioning. Let's start with the first one. If you ever write in your paper a sentence that states, results showed that there was a significant effect, then you would have, that would need some correction, because that sentence in itself will never ever have any meaning. It will never teach anybody anything unless the sentence continues. For example, the results show that there was a significant effect of another. As you mean. So the upper part of the sentence should not stand on its own. It's going to have to be corrected. A slightly smaller example is, we do often find that somebody writes, "We proved that," and then comes the conclusions from the data. Careful, in statistics, we do not prove. We leave that to the mathematicians. In statistics, we make hypotheses or estimates, suggestions, if you like. We don't prove. So, so that's also something to be avoided. Then some sentences that I see quite often is the following: treatment A had a larger mean than treatment B, but it was not significant. That's very common. And also in a large extent, to a large extent, it's also very understandable. But in one sentence, we have two messages. So if treatment A really had a larger mean than treatment B, then it would have to be significant. But if it is not significant, then the differences between the two means is coincidental. And you have to, unfortunately, bite the bullet and accept that. So don't write two things in one sentence that actually contradict themselves. One more minor thing. This you'll see often in papers too. Treatment effects were significant, and then comes a p-value, and it has just all these zeros. That's not very, that information doesn't do much. You could just as well cut it down a bit and say it's less than 0.0001. That's good enough. So so we don't want to impress with too many zeros behind the p-value when actually the conclusion is set at a much lower value already. So it doesn't make it better, or it doesn't even make it much stronger either in a case like that. And the last one of this example is probably the one that I find the most interesting one. Here you must think with me. You must maybe put your mind to this. I'm making a statement where I say there was an 80% higher risk of getting a specific disease when people did certain things. So there was an 80% higher risk of getting something. That's huge. But let's look at the numbers. If the percentage value of getting it increases by 80% from 0.001% to 0.0018%, it may have increased, but it is not meaningful. Or in a similar way, if you play 2 lines in the lottery, then your chances of winning changes from 1 in 15 million to 2 in 15 million. 2 in 15 million is still a small number, no matter what. So when we use percentages in write-ups, we should always attach the actual figure to it to say, what do you mean by something like the 80%? Very important, and you get to see that often in medical journals, for example. If that is written like this, then it usually gets returned, and the editor will mostly say, "No, I want to see the real figures, not the percentages," because percentages can be very, very confusing. But one more thing when graphs go wrong. These 2 graphs here are based on precisely the same data, except that the scales are completely messed up, because in the left one, the scale starts at 950 and goes to 1,000. In the right one, it starts at 0 and goes to 1,000. So if you have a wider scale, quite clearly, then you will see a much different variability in your data set. And anytime you do a graph, you must just pay attention to that and make sure that the scale actually does justice to what you found. It's time for me to come to to 2 slides of overall conclusions. But what happens now is not new. So for your studies, know your topic and the literature before you design it. When you do a literature search, pay attention to what you call positive and negative results. In other words, people like to report positive results more often than negative results. One has to be careful with that. Somebody writes, in a third example you gave, would it be more correct if it read X had a larger mean than Y, but the difference was not statistically significant? Yes, you could write that, but you must still ask yourself whether you may run into the danger of misleading the reader by first saying that something is larger than something else and then continuing by saying, but actually it isn't. So it is then better to write something like, there was no statistical difference between those 2 means. End of story. And then you can provide, say, in a table, what those means really are, and let somebody else look at them and maybe find interesting conclusions in this. Dependent covariates, what could covariance mean? Oh, okay, so a covariate is a second variate that you have in your study that provides an additional information on what is the relationship between dependent and independent variable. A covariate can be something like you test, say you test people's preferences for food based on gender, and then you might later add to it that it is not just the gender that maybe has specific preference for food, but it's also the age of the person. So you can reanalyze this and design and use age as a covariate to test whether it actually has an effect on your outcome or whether it doesn't. So identify the type of data you have, extremely important, because that determines what test you use. And then know your variables and your confounding variables. Make sure you have your hypothesis done before your study. Design a study and randomize when possible. Last thing being, work out which test you use. There's books that you can look up doing this. Don't hesitate. Call the great statisticians. Also at Rhodes we have them, and conduct a study and avoid biases as much as possible. And when you do your data collections, prepare a good data sheet. And I know you probably think this is ridiculous when I say this, but make backups. I'm serious about this. I've actually, a few years ago, we had an honor student who was unfortunately who had a fire in the digs, and both the computer and the backup hard drive were in the same spot. They were both gone. So that was the data. That was the only backups that there were. So I cannot emphasize enough that backups must be in the same room as the actual computer is. So and whenever you have comprehensive notes, it will make everything a whole lot better. When analyzing data, proofread. Do not remove outliers unless you're really sure that you know what you're doing. And finally, a lack of a significant effect is not a negative outcome. So don't be discouraged if you find that. Yeah, cloud backup. Yes, absolutely. Cloud backup will also work. But any kind of backup, particularly I was thinking of sometimes handwritten notes. It matters. It really does matter. After a year of doing a study and then losing them all, and I've seen it before on a few occasions, you just have to keep in mind that it wasn't a big effort to make backups, but it's a big loss if you don't. Yeah, perfect. You keep a research journal and you write down everything you've done so you can write your methods later. Finally, you have now stayed with me for so long, and you tuned into all the stuff that I've talked about. Let's have a little bit of fun and see what happens when scientists design a fun observational project. This is real. So this is based on true research by a group of psychologists. We're almost done. Let's solve the traffic jam of people at the door of a party venue. There's a door and there's a jam of people. How do we do it? So using some clever observational studies, the researchers came up with 3 steps: bait, distribute, circulate, which means step number 1, the drinks are in the corners of the room. That already distributes people into 2 corners. The traffic jam is just about to loosen up. The snacks are in the middle of the room. That would be distribution. So the distribution increases widely. And the 3rd step is to make circulation from beer to wine to other, so people move round and round and round. So with this kind of thing, maybe that might be even useful for social distancing, but at the time it was done, there was no COVID. So so the point here is that sometimes observational studies, researchers have a bit of fun, and they can go out and party afterwards. This is actually the end of the talk, but I see, James, you got one more question. Could lack of significant effect be the thing that you're looking for? Yes, for sure. For sure it can be. Or sometimes perhaps it is not, maybe it is not what you're looking for, but it is what you should be accepting as something that is more valuable than what you actually originally wanted to look for. All right. A very, very simple example is that if you test something, if you have an instrument, for example, and you must do, say, a calibration curve with your data set, then you actually want your data to go through a 0 point, which means that your model that you get is not significantly different from 0, but that's exactly what you do, but that is exactly what you did want to get. And sometimes the lack of significance is actually a positive thing, particularly when it has a good outcome about something. However, your problem is, and that is not just yours or mine, but our problem is that a lot of submitted papers to journals will not have the right kind of reception if they don't find what is the famous significant difference. And that's very sad. So sometimes we're actually missing out information. And so your question is brilliant, because we're missing out information when we ignore that. Of course, a lack of significance can also be a direct result of a too small sample size. In that case, you're not looking for that. So it is a bit more complex, but you're quite right. Don't ignore it. There's value in it. There's definitely value in it. So having reached this point, yeah, it's up to you now. But I'm leaving you so that you can maybe go party and have no traffic jam at the door. Thanks for everybody to listen.
Thank you so much, Horst. I've learned quite a lot from this session. I'm always keen to figure out more about how scientists write, because this is not something that I necessarily know a lot about, but I'm often asked to help science writers. If there are any final questions or points, please do post them really quickly. Otherwise, you offered last week, may people still send you an email if they have any questions based on the presentation afterwards?
Yeah, absolutely. No problem.
Oh, okay.
No problem at all, except for maybe one smallish thing, and that is that anything that has to do with a specific project, we must always remember that that is between a student and a supervisor. But if
Yes.
it's like interesting questions or thoughts or something, that's different. That's absolutely great.
Grady did ask if there are any sort of references to, I suppose, textbooks or papers or maybe even online resources that you could share so that they could sharpen their skills. If there's anything that you recommend for your own students.
I came across a very nice site, and that is called. I can send you the URL for it. It's a person who is a statistician, but he wrote a few books of making statistics accessible without a formula. So he was basically just using intuition, basic ideas and stuff. They're nice, and if anybody is interested in this, I can then send you the URL, and you can see whether you can get those.
Sure. Okay. If you can send it to me, then I can share it with the people who hear.
Yeah, perfect. It would take me too long now to find it in my files, but I can send it to you in the next couple of minutes.
Sure, I'm happy to follow up. But otherwise, there's just lots of thanks in the chat for your time and for these inputs.
100%. I enjoyed it.
Well, so did we. Thank you all very, very much. Enjoy the rest of what's left of your week and your weekend. And hopefully we'll see you in a few weeks at the next seminars coming up. Thanks, everyone.
All right. Thanks, then. Bye.
Thank you. Bye.
Bye.